Hi, guys. A couple of people emailed me about plotting courses and celestial navigation, and they just had some questions about it based on my previous couple of videos. And also, I kind of spoke with Rick again, just on YouTube on comments on his video. And I wanted to try to clarify some things for people who had emailed me. And I'm going to try to do so without using a lot of complicated terminology just so that you have a better understanding for those of you that are not used to coordinates and how we navigate the earth and how we would navigate the celestial bodies in the sky. The first thing I want to explain here is right now I'm looking down on the North Pole. Okay. These lines that extend from the North Pole down to the South Pole are called lines of longitude. And the lines that circle the globe are called latitude lines. And as you can see right off the bat here, the distance between the latitude lines, it does change slightly when you get down to the equator, but not by much, not really enough for us to be concerned with. The lines of longitude clearly are widest at the equator. They cover longer a distance in the same amount of time, okay, than you would as you get close to either the North or the South Pole. You know, navigators know how to account for that stuff. And of course, I'm not going to get into this, but this is right now all working with true north and true coordinates. The magnetic poles are not exactly where the true poles are. So you have to, when you're using a compass, you have to account for that and you have to adjust for errors that you're going to get between the difference of magnetic north and true north. One of the things I want to explain is right here, this line that extends out is extending out from Greenwich, England. Okay. That is UTC or Greenwich Mean Time, GMT 0. So this is what everything is based on. Okay. This line on this side, this yellow line, is called the prime meridian. So that's where time is 0. The longitude stuff is all based on time. Okay. And as you can see, as we go west along this red arrow around the Earth, we're moving in a negative direction UTC wise. That's why when you look at the United States on the East Coast, for example, we're -5 or -4 hours, depending on whether daylight savings is in effect. What that means is we're 4 hours behind Greenwich. Okay. So whatever happened in Greenwich at 0 time, you know, it's going to take 4 hours or 5 hours for us to see the same things. Okay. That's where the negative UTC. Now, if you go left of the prime meridian or east of Greenwich, England, you're going to be going in a positive UTC, and that's an easterly longitude. Now, the longitude numbers go clockwise, beginning at 0, and then they go clockwise and increase in value until they get halfway around the world at this line, which is called the anti-meridian. This is also the international date line. So the numbers will go from 0 all the way to 179 degrees, 59 minutes, and 59 seconds. 180 would technically be this line. Once you go past that line, now you're counting down. This would be, going from 179 degrees, 59 minutes, 59 seconds, all the way down to 0 again, because this time we're dealing with east longitude. So it switches from being a negative UTC when you're dealing with time all the way up to this point around the world. And then when you're over here, we're going to be positive UTC because we're ahead of Greenwich Mean Time. So in other words, that would explain why, Australia, for example, would be considered a day ahead of us, right? So just keep that in mind. We're starting out here at 0 time and 0 longitude. And then we're going all the way up to 180 longitude. And if you were going east, it's the same thing, 0 longitude all the way around until we get to 179 longitude. That's how longitude and latitude work on the Earth. Now, one of the things I want to mention is, let's say you were standing on the Earth right here, and some object, some celestial object, I don't know, it could be a star, it could be the moon, or whatever, and you would sight that through a sextant, okay? When you're at the horizon, the minute it appears above you can't see anything that's over here, right? Because it's below the horizon. So the minute that star appears, that would be at like your zero altitude. So how high, is that object in the sky from the point of view of the observer? So over here, since you're on the ground, you're at zero height. So the altitude of that object will be just rising off the horizon. And of course, as the Earth turned and time went on, that object would slowly and slowly appear at a higher altitude from here, because this brown line would be extending out. That's what the sextant is measuring. The sextant is measuring how high from the observer is the object that you're sighting. So it's giving you this line here. Now, let me switch to another screen to show you the way it works when we're tracking stars and everything, since we're no longer talking about coordinates in Earth. Earth, when we're talking about positions, we're using longitude and latitude. Okay, now this is a different shot of the Earth. This time, I'm looking at the anti-meridian. So I'm 180 degrees away from Greenwich. It's on the opposite side of the Earth at that point. The brown line that I had is now green. And let's assume that the X that I had was the sun. And let's assume that if you were at this point right here and you sighted through your sextant, the sun, just as it was rising, just as the bottom of it got above the horizon where it looked like it was sitting on the Earth. That's what the sextant. So that would be at zero altitude if you were at sea level. Obviously, if you're higher in altitude, like in an airplane, you're higher in the sky, you're going to notice the sun coming above the horizon quicker because you're taking your sight from a higher position. Okay. Now, the stars and planets in the sky, when they're in the almanac, they kind of use a system similar to longitude and latitude. Now, if you imagine the Earth, there's an imaginary sphere that would encompass the universe. Okay. And all of the stars and planets are projected out on that sphere. Now, although the stars move, they move for very, very, very minute amounts. I mean, it could take light year, years, hundreds of years before this star will even move in the sky, an inch or whatever, right? So it's only something that a physicist might need to be concerned with. If you're navigating, you don't have to be concerned about the movement of the stars. But what you are concerned with in the almanac is they use a body, specifically Aries, are moving at a high rate of speed. So we track them in the almanac. It'll show the moons and the planets and where their positions are relative to the time of day and your position on Earth. What they do for the stars is they pick, like I said, Aries, and they give you the celestial angle on the sphere, or the distance, let's call it, of that celestial object, the star, from Aries. So those numbers really don't change much, like I said, over hundreds of years. That's why they're able to do that. And what they do, as I said, they don't use longitude and latitude. They use, and I might be wrong because I don't have any reference material here, but they use declination, and then they use, it's called GHA, which would be an angle measured from one of the poles on the celestial sphere. Let's just say it that way. Again, I'm trying not to make things really confusing for you. I'm trying to make it easy. So this is what the sextant would do if you're on a plane or a boat. This red line is Amelia Earhart's projected track, and right here is where she wanted to land. Right here is where she took off. So you're using the sextant to calculate a line of position in order to estimate where you think you are on the globe. And the sextant is only part of that. That's going to help you determine the angle. So in the almanac, if you look at this line on that specific day, and I'm going off of memory here, I think the sun, based on the position he gave, would rise at roughly 67 degrees from the North Pole. It would appear 67 degrees in the sky if you were at this position. So that would be where he would look for it to calculate this line. Now, this green line actually goes off into infinity. It comes down and it goes all the way up. So he knows at that point that he's somewhere along that line. And then what he would use is another object, okay, to make a second line of positioning. And where those lines would cross would be his location. Now, the lines of position, when you look at like where Amelia Earhart's navigator thought that he was, the first line, the lines of positions are going to be completely perpendicular, or 90 degrees to the angle of the site that you have in your sextant. So he can plot that line, and he's going to assume where he is at that point. So basically, he's going to take that line and swing it around so that it's perpendicular. And that's how he creates this line. So if this is 157 degrees, the other point would be the reciprocal, or 337 degrees. And it's perpendicular to the object that he cited. Then the other thing that he would do is he would use another object, and he would do the same thing. He would have his azimuth, his altitude to that, and then he would draw a perpendicular line to that object that would go this way. So if he was using Polaris, which he wouldn't have used because you can't see Polaris from over here, if this is Polaris, you can only see it north of the equator because of the curvature of the Earth. That's why they use different stars. For example, this star here, let's say, might be Fomalhaut that I talked about on my other videos. Obviously, I don't know that. I'm not looking at an astrological chart, but he knows this. Fred would have known this. That's what Fred would look at. And as you notice again here with the longitude, these are west longitude, 130, 150, 170. And then it starts counting down when it crosses the date line, 170, 150, 130. Okay, but you'll notice that we're east. So as you can see, you can't just say I'm at 150 longitude because you have an east longitude, then you also have a 150 west longitude. Now, the altitude I explained, the azimuth, okay, is the angle from the north and south poles. And it too is measured clockwise. So you would not use the sextant. You calculate the azimuth using the information that you have on the charts of where the object is expected to be from your point of reference. And as I said, the angles that you read in the almanac are all measured from this point at the poles. And then it goes clockwise all the way around up to 360 degrees. So this isn't based on time. Azimuth goes from zero, around the poles. Okay, it's an angular measurement, but the angle is actually not really measured from Polaris. It's actually projected out on the celestial sphere. And like I said, I don't want to get into all of that complication. I'm trying to make this easy as possible. If you look at the light, I have the sun turned on. You can kind of see that this light that's coming up over the horizon as the sun lights the earth matches the angle of the line that I have here. But the problem is, as I said, the longitude is based in part of time. So, and it's based on where he thinks he is. I could take that same line and I could draw that line over here. I can also draw that line over here. And obviously, the time would be different. As the sun is coming up, this line is slowly going to be moving to the west. So if you're wrong with any of your estimates way back here, your estimates are going to be increasingly wrong. That's where we can lead to errors. I'm assuming with Fred Noonan that he didn't make these kind of errors because he wasn't an amateur. He pioneered celestial navigation from the point of view of an airplane. Celestial navigation was used for a long time. I mean, back to the 1300s, I think they used octants, they called it, and then eventually they became sextants. It's a really interesting history, and there's a lot of cool videos out there that you can watch that tell you exactly how it works. But the main premise of a sextant really is not that difficult. You basically look and try to locate that item. The sextant is level. Some of them even have a bubble level on it. So you're parallel with the Earth and you're at the surface of the Earth and you're calculating the distance of the objects from the horizon line. How high are they in the sky? And then you're referring back to the documentation to get the angles. And then you're creating a line of sight and you know usually within a couple miles, let's say, because it's not really that accurate when you're using, especially when you're on a ship and the ship is moving, the airplane's moving. You're going to be, let's say, within 10 miles of where you think you're going to be. But the problem comes when he takes this position and he then needs to translate it to a chart or a map that he's using locally. So if his estimate's wrong, the position that he plots on the physical surface of the earth is going to be wrong. So let me show you how that would come into play. It's easiest to do this probably in Google Earth, and I'm going to use the Amelia Earhart flight as my example. But here you can see the celestial bodies. It's not accurate in Google Earth. You would be better off using an application like I showed you before, the Stellarium, for example, to do that. And then you just check your results and plot them in Google Earth. You know, Polaris is sitting up here, and then what he would do is he would pick another star out of the bright ones, and he knows where that is based on the constellations, what he's looking at, and then he would calculate the altitude of that one using the sextant. So he would basically create those lines of position. And as I said, the lines of position are going to, the one for the sun, for example, I had was showing like that, right? The object that he sighted in the sky, this line is perpendicular to that line. So he knows that he's somewhere on this line. He don't know whether he's down here or up here, but he's somewhere on that line. So if you track another object, okay, that's basically going to create another line. So if you track something up here, for example, that would make a line coming down. And then if you create a perpendicular line to that, okay, then he knows that he's somewhere along this line and this red line. So what that means is when you get in here, where those two lines intersect is right here. Okay. Now, obviously, don't pay attention exactly because I'm not being precise here. So don't think that Amelia Earhart's ship is right here. But that's basically how it would do it. But if you look here, you'll notice that there is a triangle being formed. We have this point, and I have this line going out, and we have this line going out. So we have one leg of a triangle here, another leg of a triangle here. If I were to pick another star, and then I would get another reference to that star shooting down this way, and then make a line that's perpendicular to that, we know that he's somewhere along that line and this line and this line simultaneously. But if you see, we have a triangle in here, all right? So he could be anywhere within that triangle. So you could measure the distance of that. And usually, if you do this accurately, the distance of that triangle, the smaller you can make that triangle, the more accurate your prediction is going to be. So right now, he thinks he's here, but he might really be here. He could really be anywhere. He could be down here, here, anywhere within this triangle. So, like I said, his goal is to make that triangle as small as possible. And when he's calculating his first line, the problem is that he's using his previous measurements as the time went on in the flight. So if he was wrong, his error would get progressively wrong and wrong and wrong and wrong. He could become off course, which is going to throw everything off. And that's what I believe happened, because one of the ways when he pioneered celestial using the sextant in an airplane and celestial navigation was that he did it for Pan Am on their transatlantic and trans-Pacific flights. All right. Because the problem is at night, you can't really use dead reckoning. There's no radar over the ocean. And a lot of the island stuff are uncharted. There's nothing predictable that you could use for dead reckoning. But what they do on a commercial airline is they know how to use the radios, and they'll communicate with various stations. And then they could measure the signal strength and triangulate where you are based on the signal strength of the radios. So that gives the navigator another point of reference. Okay. That's the fix. That's the fix that Amelia Earhart was constantly trying to get. So if he did his triangulation with his LOPs, okay, and he had his triangle here, he's going to take the com references back and plot their information on the course, and that'll help him reduce so that he knows where he is. So when he was on a commercial flight, he would never be too far off from his course because he was continuously correcting for the errors that he may have had. And the problem with Amelia Earhart is they were having radio issues, and compound with the fact that they didn't have a single point of reference that was quote unquote managing this flight, is you really didn't have any standards. You had people from different time zones creating errors by giving you different time reports. So when she was trying to calculate headwinds and the weather reports and stuff are wrong, she might have not known her true airspeed. So if he's trying to use dead reckoning based on airspeed, that could have been off because she knows based on her compass the magnetic north, not the true north, the magnetic north that she's facing. But there's drift due to the airplane itself that causes the compasses to be inaccurate that she needs to take care of. We don't know if that happened. But of course, the navigator would also look at it and he would use that to cross reference. So he knew her altitude, he knew her basic heading. But that doesn't matter. She could be heading in this direction down here. I mean, I could draw this same line at the same angle, compass angle, and she's still headed in that same direction, but she's off course. And she may not know it. And the wind could have been slowly blowing her off course, and they never got corrective measures. So and the funny thing is, like I said, and I'm not the first one to point out, but the point at which she communicated that she was 200 miles out just happened to be when they crossed over the dateline I just got done talking about. And that is where we switch from positive longitude over to a negative longitude. So when he was transferring his measurements to the charts, did he make a mistake in his estimates? So that's what we need to find out. We need to kind of use the stellarium, for example, and track the stars on that specific day. Because although we don't have the pilot's records from the flight, because they never made it to the destination, what we do have are computer simulations of the sky that he would have seen. Now, you'd also have to factor in aberrations due to the atmosphere around the Earth and the clouds and the weather. So it becomes very, very complicated math when you're trying to do exactly what I'm telling you to do. But it seems obvious that this is where he got thrown off. But what I'm assuming is that he slowly got off course, and that would explain why the ships never seen him. So his course may have actually went over this way. Okay, so he was, let's say, 100 or 200 miles south of Baker Island when the sun rose. And that was the other thing that happened right here. Okay, the sun rose right about when they were over here. And we know for a fact, because we're switching to daylight, where there's no objects that he can observe in the sky other than the sun and sometimes the moon, he was absolutely going to calculate the angle of the sun. Absolutely. And he probably did that just as he was approaching this point. Okay. So the last point he reported to Amelia was that they were 200 miles out, which puts them here at 1745 GMT. It puts them here. But what I'm wondering is, were they really down here? And that would kind of explain why the natives over here didn't see the plane, but they heard the plane. That's because they were south. Once they got past these islands over here, there are no other islands other than this island. So if they were on a 5737, and I'm not going to try to be accurate here, but they thought that theirs crossed over Howland Island, right? But what if they thought that this was that line? So when they said that they were going north and south, they were flying north and south here. You understand what I'm saying? They were flying north and south here, trying to locate Howland Island. But if they were down here, they probably crashed in the water. But if you look, there are two uncharted islands down here. There's probably more that might even be tinier, and Google Earth didn't pick it up. But she could have thought, look how similar they are, Howland and Baker. So when she was going north and south and she tried to turn back on course, she could have thought that she was heading northeast, but she was actually, she could have thought she was heading east, but she was actually heading northeast, mistook this island for Howland Island, mistook this island for Baker Island, and said, screw it, we're going to land here. And let me put a point there, just so that you guys could see it out there that are on the websites. Here are the coordinates of that point. So take a look at that. They could have flown to here, certainly had enough fuel, and that's where I would have looked. So I don't think they ever crossed the equator. I don't think they did. I think that they went into the ocean down here, because she wasted her fuel flying, let's say, up to here and here. And it was daylight by now. And the only way for them to use dead reckoning in daylight to actually see these tiny islands, because you can look here, I'm at an high altitude of 887 miles, 887 miles in the sky. She was only at 8,000 feet, So they're seeing nothing but ocean as they fly around here. And their only object is left in the sky is the sun and maybe the moon. But in order for him to use just one object, he would have to spend, let's say, an hour and track that same object over multiple sextant altitude measurements. And then he could calculate where that object was moving in the sky, and then also use, the South Star wasn't even visible at that time. So their orientation would be completely off. So they're using that, that star over multiple times, flying at a low altitude. She's burning more fuel, a lot more fuel. If she was flying like a few thousand feet, 2,000, 1,000 feet above the ocean, she was burning a ton of fuel, which would cause her to go into reserves and possibly run out. She never found land. And if she thought, like he was saying, that they passed the equator, then she wouldn't go above here to go and look. She would only probably come around to this point, right? So her plane would make sense to be somewhere down here. And if you look at the pattern of Howland and Baker, just from a dead reckoning standpoint of view, these two uncharted, unnamed islands kind of look very similar. They're almost the same distance apart, even. Okay. The only difference between them is the angle. But like I said, she might have thought she was flying east at this point, but she wasn't. She wasn't, because the only time she was probably paying attention to her compass was when she was up around here. So she knew she was flying northeast here. Okay. So when she's down here, she's still flying northeast, but at a much steeper angle. So if they did cross the equator, they would have done so way out here. And now this is west of them. So now, I mean, they're really screwed. So that would be my estimate of where they went down on that island. Okay, right here. And again, I'll show the point there just for you guys. That's the point of that island, and the other island is right here. In case you want to reference those points by yourself. And the point at which the antimeridian crosses the equator, you could find that out in Google Earth. Just go to view and turn on the grid. It shows you that. So you can plot that point. Okay. And the ministry, where it intersects, is right over here, roughly. So she would have been slightly north if she was on that path. I believe they were south of it. I don't think that they went north. And the reason why I'm saying that is because neither of these two ships seen her plane. And this guy might have been wrong when he said she's 60 miles south, when he was trying to use the radio. Now, remember, if you go back and read the transmission, her signal strength was not that strong. So he may have not been accurate when he was calculating her southerly position. Now, she said she's seen the ship. Well, she could have seen the ship from 8,000 feet if she was here, but she also could have seen the USS Ontario if she was over here. You see what I'm saying? And I want to point something else out. Although this is a straight line, her path would follow the curvature of the Earth. So that's why, like when planes are flying to Hawaii, they don't go, if you were flying from Florida to Hawaii, you wouldn't just fly in this direction. It doesn't make sense because the distance is too long. You could shorten that distance by flying up towards the pole and then coming down. So you would fly at an angle like that. So anyway, that's it. I hope that makes things clear for you guys. These are the guys here that do basically have track all the research on Amelia Earhart. Okay, Tighar. This is the group that guy Mike Cameron had helped, and he always had a flight ready to go if anybody spotted where they thought the plane was. He's passed away now. His wife is still alive, but he was really interested in Earhart, and that was something that he shared with Forrest Fenn. I wish they were both alive because I would love to have been able to discuss this with both Mike and Forrest. And like I said, people took notice of the fact that this error happened right at the international dateline and the intersection of the equator. Everybody noticed that, but nobody's actually tried, as far as I know. Nobody's used the Stellarium website that I showed you to try to track where her plane went and actually use the stars and navigate as he would have. Okay. But like I said, you're going to have to take a lot of things into consideration. And there's a lot of trigonometry involved. It's pretty complicated. You really need to understand how celestial navigation works. And I just wanted to try to do this in layman's terms to make it simple for everybody. So I hope that that group Tiger comes and looks at what I point out, these two islands down here. This is where if she did land on an island, she might have went to these two, or there could be other uncharted ones down here. If not, I believe they just simply went in the ocean because she ran out of fuel flying along the 157, 337. He might have thought that he was here, and he wasn't here. And it was completely wrong, especially once they got to the point where she switched into recovery mode going north and south looking for the target island because the sun was up now. At that point they got way thrown off and there was no ships anywhere near to get there in time to try to figure out. So if they went down in the water, they went down pretty quick. And if our focus of trying to find them was back here or north, or they went from this location and worked their way east, by the time they got here, the plane was already under the water and they were dead, unless they made it to land. But as you can see, there's other islands even way down here. I don't think they would be that far off, though. But there's probably many uncharted islands along here. Which ones did we actually research? I don't know. Maybe these guys would know. I haven't went through all of their documentation. I'm gonna make them aware of my video because maybe it'll become of some help to them or some use. These guys certainly did a lot more research than I did. In fact, they have databases of all of the research, and I use some of them to locate these points that I found here. But what I couldn't find on there is anywhere they were going to try to plot his course using a celestial navigation to help navigate, to try to figure out where he might have been. I know they've done that up here. But when they did that, were they using only the radio? Or did they actually delve into possible locations that he went off track? And did they actually go back in time and look at the almanacs and physically put themselves here in a simulator, in a computer, at different positions and look at the sky to see where Fred made his error? Because as I said, I believe this is Fred's is the one that got them lost. And then everything just started compounding when she was looking around, and then ultimately that caused their demise. So, but have a good day, folks. Peace.